All right, so we already talked about semi-log plots. It was actually not lesson 5.4. It was topic 2.9, but last year I labeled my units differently. But anyway, it was the same thing. We just called something different. We talked about semi-log plots where the vertical axis is logarithmically scaled. And so I think you recognize something like that. That's what the grid looks like. And we did this exact situation where this is the graph of the population of English Americans in the United States from 1620 to 1820. And if you look at this, it looks like for the first, 80 years that the population didn't really do much, that it stayed the same. And so what you can do is scale it differently, and you can see that during those first 80 years, the population was actually increasing. So this is just another representation of the same values. And one thing to keep in mind that is important is this statement right here. So with a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. And so this first example, we need to use that idea to answer the question. It says to use the features of the semi-log plot above to justify why an exponential model is appropriate for the population of English Americans in the current United States during that period of time. And so if you look at like after 40 years, what does the graph appear to be? Linear. So when the semi-log plot appears linear, then the exponential model is appropriate. So let's jot that down. The semi-log plot appears linear after 40 years. So the exponential model is appropriate. And I feel that the AP test is going to find a way to test that you know that. It's possible it might be like example 2, or it's possible that it might be simpler that you just see the graph of the semi-log plot and then ask like which model would be appropriate, and that it would be like linear, quadratic, exponential. And so you would have to know that when this appears linear, I don't know what I was about to say. Right. When that appears linear, then the model is going to be exponential. So this data is from Mr. Passwater telling jokes. And the joke begins to spread through the school. The number of people, P, that have heard the joke, T minutes, is graphed in the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? So we just said that the model should be exponential. Hey, Briar, put your phone away, please. And so what models can I mark out on our answer choices? Or what choices? The linear, choice A. Anything else? And C, the logarithmic. This model should be exponential. Both B and D are exponential. So how are we going to decide which one of those is it? Plug in. Or look at the choices. So yeah, that's exactly what we're going to do. So this right here is when T is 0. What is the value of how many people have heard that joke at time 0? 2. right, I'm going to use one more point. What about time 1? 4. So for the correct answer, we should be able to put 0 in and get 2, and put 1 in and get 4. And so you can probably do that in your head. So that ends up being 2 plus 1, which is going to be 3. So it's not going to be B.
Can you just hand these to the kids, like the ones that have the name?
Sure. And then let's check D. So we'll put 0 in. So that's going to be 2 times 1, or 2, which is good. And then just to be double sure, we can plug in 1. And 2 times 2 is 4. So it is choice D. All right, any questions on that? Okay, the next couple of examples are mainly just being able to pick out the ordered pairs or graph the ordered pairs on the semi-log plot. So just to let you know, an important note is that whenever you logarithmically scale the vertical axis, you're not changing the values. So like the value of the function, if it was 2 here, it's also 2 here. So you're not changing the values, you're just changing the appearance of the graph. So whenever the graph is logarithmically scaled on the vertical axis, if we're equally spaced, like what we had here, equally spaced, then from one point to the next, that just means that those y values are proportional, and then the equally spaced x values are linear. Okay, so we have this table of values. We're actually going to use the same table on the very last example also. And it doesn't tell you what type of function it is. We could probably figure it out by looking at the y values, but we want to pick out which semi-log plots where the vertical axis is logarithmically scaled would represent those values. Okay, so is this first one a semi-log plot where the vertical axis is logarithmically scaled? No. Is there an axis that is it's so hard to say, logarithmically scaled? The x-axis is, the horizontal axis is, but that's not going to be the right graph because it's just messed up. So we're going to say vertical axis not, and we'll just say log scaled. The horizontal axis is, but this one tells us the vertical axis is the one that needs to be logarithmically scaled. All right, what about C? Is C logarithmically scaled anywhere? No. All right, so we don't even need to worry about those. There's no possible way they are going to be our answer. However, C and D are both have a vertical axis that's logarithmically scaled. So at this point, we would want to look at the values. So when the x is 1, the y needs to be 40. Well, this one just goes from 1 to 10. Is there any way that that's 40? No. So it is going to be D. So this is a question. If you know anything about semi-log plots, you should be able to quickly pick out the right answers. And so this is true. So this is 40 because it's like 10, 20, 30, 40. This is 60. This is 90. So it's the perfect one for it. All right, any question? All right, let's look at example 4. This is what we did before. We had the logarithmically scaled grid and we graphed some points on it. So we're going to do that again. So we're going to start when x is 0 and we're going to graph at 200. So we go up to 100 and then count the next line would represent 200. All right, whenever we did this the first time, I don't really like what I said to you, and there's some people in here that really listen to everything I say and say it right back to me, and then I realize that what I said might not have been exactly right all of the time. And so it's one like on B. When we want to graph 25, before I would be like, oh yeah, it's just right in the middle of 10 and 20. But do you think it really is on the logarithmically scaled? So if we would look at from 1 to 10, which number would be right in the middle, do you think? The closest to the middle? 2 is here. Probably 3. 3 or 3.5 would be what is right in the middle. So if we really wanted to graph 25, it's going to be a little bit above the middle. Now, I don't think it's going to matter. If you still do it in the middle, it's going to be fine. I just feel I don't like what I told you that day. Just want to make it right. All right, then let's look at 2, 7. So that's not going to be hard because we can actually count to 7. I'm having a hard time seeing all the lines. There it is. All right, and then 4.6 and 1.5 is going to be a little above halfway. All right, so what questions do you guys have so far? Okay. So this last one, what we're going to do is actually take this same graph from example 3, and we're going to write an equation for the linear model of the logarithmically scaled graph. All right, so the linear model for the semi-log plot, you'll have the slope in front of x, and then this will be the y-intercept. The base is going to be the base of how it's scaled. Typically, I've only seen 10. I've never taught statistics, so these graphs are way more common in statistics. But this, for what we're going to do, this base is going to be 10. And so we can get a linear graph for that, or a linear model for the logarithmically scaled graph. Okay, so let's just start off with the original points. And so we have the original points on a previous problem. You could still get them from this one. Let's hold a space for 0 because we're going to need that in a second. But from the original graph, we have points for the x's 1 through 5. And this first one is 40, and then 60, and then 90, and then 135. To me, doesn't really look like 135, but that's what the data had. And then 203. All right. Now, if we want to get the equation of the semi-log plot, the ordered pairs we're going to use are not going to be these, because they would give you the equation of exponential. If we want the semi-log plot, what we need is the log of the y values. So there's two things we need to get the equation of a line. And that you haven't done a ton of equations of lines this year, but you definitely did back in Algebra 1. Well, I guess we have done a lot. Not necessarily in slope-intercept form, but we are definitely going to need the slope. So if we're going to find the slope of this line, what do I need to subtract on the top? The y's. In this case, is going to be the green y's, actually, the log of y. So we would do, I'm just going to use the first 2 points. So we'll do log of 60 minus log of 40 over 60 minus 40. Just kidding. What does it need to be over? Does still need to be x's. 2 minus 1. All right, now this one works out a little easier than one of the ones you guys have to do, because on that denominator, that's just 1. And so it's log of 60 minus log of 40 over 1, which we don't need to write. But for my slope, I just need it to be log of something. I need a singular log. So what am I going to do to bring these together as a singular logarithm? Divide the arguments. Good job. All right, and then I would probably reduce that down to either a 1.5 or 3/2. They're both perfectly acceptable. All right, so if the slope of the semi-log plot is log of 3/2, what that means is this is going to be linear. So on linear, to get the next y, are you adding something or are you multiplying? For linear, you're adding. So what we're technically doing is adding log of 3/2 each time. And it might not feel like that's what you're doing, but if I took log of 40 and I added log of 3/2, that says log of 3/2, you can't tell. What would I actually, if I wanted to bring those together as a single logarithm, what would I do with the 40 and the 3/2? Multiply. And when you multiply 40 times 3/2, you get 60. So log of 60 would be the next one. And then same thing, you would add another log of 3/2, multiply 60 and 3/2, and you get 90. So that is really the slope. So what do you guys think you're multiplying by each time on the blue column? It's in your problem. We've just wrote it at least 2 times. Not the log, just the 3/2. So 40 times 3/2 is 60. 60 times 3/2 is 90. Just like it was in the other column. Okay, so I'm going to get started. This is kind of a tough concept to understand. But our slope of the linear model is log of 3/2. That's going to go in front of x. All right, so this one didn't give me a y-intercept. I could guess about where it's going to be if I continued this line. But I can actually find it. So if on this column I'm multiplying by 3/2 each time, what would I do to go up? Divide. So someone who has their calculator out, take 40 and divide it by 1.5, please. All right, and then what is that as a fraction? 80 and what? 80 over 3, good. Now, if it hadn't been a decimal that just kept going, it would be fine to put the decimal there. I don't like the repeating decimal as a answer. All right, so that means for the semi-log plot, the y-intercept is going to be log of 80/3. All right. Okay, and then both of those translate to the exponential model. So the a we got here for the intercept is the same a, that's the initial value. So that 80/3 is going to go in the front. And then the 3 halves that I got when we're multiplying by each time, that obviously is the base. And it's raised to the x. So the a and b translate to the other a and b exponential form. All right, now this gets slightly more difficult. There's one you have to do whenever there ends up being a number in the denominator. So I'm going to see what you guys can figure out with that on your own, or looking at the answer you might be able to figure out what I did. All right, so if this last one like totally stresses you out, I have seen, I don't know, probably 150 different possible free response or multiple choice questions. I've never seen that before. It doesn't mean it won't be on the AP test. It just means it's unlikely that they'll throw that on there. So it's a good, I don't know, introduction to something you might have to do in statistics.